All right, so next up in our process is to chat about the MD checksum. So the big goal of this is that we're going to be constructing 16 bytes that we're going to append to the end of our padded message. And then this thing is going to function very similar to kind of those little parity bits that we saw back in error correcting code land. Basically, if I were to just take the padded message, append the checksum, and send that thing off, if you were to change any of those little bits, then it would scream at me because that checksum would no longer match with what the actual message was supposed to be. So on their own, checksums are pretty cool. They're just not quite cool enough for the actual masking that a hashing algorithm has to do. So you can kind of think about this as two separate processes, is that I'm going to design this checksum aspect, and I could go about sending these things around, except for you're going to very clearly see what your message or password was. So it's going to become kind of this middle step is to compute that, and then it's going to go through a full-fledged compression land. So in front, you should see a little bit of Python code. We're going to play here, and then we're going to jump back to my iPad to kind of doodle around with what's actually happening. But this gets us kind of a nice feel for what it's going to look like. So if we give this a run, I've designed this to allow me to type in whatever I want. So here I'm going to feed in hello world, and it's going to print out a whole bunch of stuff. So initially, it's going to be that Unicode version of that string. So the 72, 101, and so on and so forth. That thing has length 11, so I need to pad on those 5 5s. That thing's now of length 16, which is great. What's going to happen now is I'm going to generate this nice little checksum. So there's going to be a little bit of swirling and mixing and general shenanigans that are going to go into designing that. And then we're going to append that thing at the very end of my padded message. So I'm going to have my Unicode list, the padded version of it, and then at the end of the day, I'm going to add on this nice little checksum. So as I mentioned before, you could go about just sending that thing across. If you just wanted to send some plain text that has this nice little checksum, if you were to change any of these things and then try to reconstruct the checksum, it would not compute this back end part of it. So it gives you that immediate way that, hey, we're going to have some issues. So here you can see this 146, 68, 103 all the way down to 34. So if I were to rerun this and change it to hello, let's just change it to bello world, you would see that my checksum is going to be very different. So if I were to have changed that first little 72 into a 66, the rest of the message looks totally fine, except for if I were to evaluate that checksum, it's not going to match with what I had before. So it does function just like that kind of error detection side of things. So checksums are cool like that. We're just needing to go one step further to then scramble them up a little bit and turn it properly into a hashing algorithm. So what you can see here is that we're going to create these 16 little terms. They're going to be using some of my padded message, and we're also going to be using one other cool little tool. We're going to be using what's referred to as a lookup table. And over on the left, we're going to have the corresponding MD2 lookup table, which is this big old list of 256 things. So this thing functions very similarly to those massive little permutation matrices that we just got done playing around with. Except for this one, I did not store as a 260 by or 256 by 256 giant array. Here, I'm just going to store it as one single list. But this thing's going to allow me to scramble things up very nicely. Basically, the way that it's going to work is that if I feed a 0 into it, it's going to return a 41. If I feed a 1 into it, it's going to return a 46. If I feed in a 2, it's going to kick out 67. If I feed a 3, 201, so on and so forth. So the index that's coming into that thing is then going to connect to one of these values, and that's going to be the thing that you return. So this crazy little matrix is actually then going to be that the way that we scramble some of the components up. So there's going to be a bazillion amount of XORings. There's also going to be a bazillion amount of calls of this thing, and that's going to add in some additional scramblings. So that's the game that we need to play, is how we're going to go about designing this nice little checksum, and we need to do that quickly and efficiently so that this process is not super duper slow and bogged down. So it does need to happen almost instantly. So if I say hello world exclamation point, it's got to be done almost instantly. All right, so let's jump back into my iPad so we can doodle around a little bit more. So you'll see some nice pictures emerging, but I do gotta swap screens. Struggles. Go swapping. Nice. All right. So here's going to be kind of a standard little image of what some of these hashing algorithms swappings are all about. So what you're going to think about up on top is going to be our original padded message. So that was my 11 little numbers padded with 5 extra 5s. So I have this ultimate padded message of length 16. Or maybe I have a padded message of length 32 or some multiple of 16. What's going to occur now is we're basically going to run across this padded message. So you can kind of think about this back as kind of like Turing machine days, is that I'm going to have a little needle that's going to jump across this. And at some point in time, I'm going to be staring at, let's say, the 5th entry in this padded message. So I'm going to grab that value. So I'm now holding that thing. And what's going to happen is that I'm going to paste this down into some newly constructed checksum. So you can kind of think about this as 2 little lists that are occurring at the same time. Is that I'm going to have a needle that's going across my padded message, and then there's going to be a needle down on the bottom that's going to be changing up my checksum. In our scenario, we have 16 and 16, so we're going to run across these essentially at the same time, but the padded message might be significantly longer than 16, so we're going to run across that once, while the other one then goes across a whole bunch of times. So the way that it's going to construct this checksum is that it's going to grab that current value of our padded message. We're then going to compare it to the previous value in our checksum. So whatever was stored there, we're going to XOR those 2 things together. That's then going to give me some number. So let's say they XOR to give me the value of 72. Then I'm going to take that number 72 and I'm going to shove it into that little S list. So that 72 is going to become the index. And then that 72 is going to be scrambled up and sent somewhere else. That value then is going to be updated into the current value of that checksum. In that I'm going to take whatever is currently stored in that checksum, and I'm going to XOR it with whatever emerged out of that permutation. And that's then going to be stored in my CJ. And you're going to rinse and repeat that over and over and over and over again. So to initialize this, we're going to see that process by taking my padded message, which I'm currently writing in binary, though I probably should have just done this all in just normal number land, but whatever. We're running this with a binary land. We can always convert it as we go. So I have my 16 things there. My checksum is then going to be initialized as all zeros. So my first move is then going to be my needle pointing at my first thing in my message M, or my padded message. I'm going to take that thing and I have to XOR it with the previous thing in my checksum. So the idea here is that I'm starting here and I have to go to the previous thing in the checksum. So if I'm at slot 0, previous would somehow be -1, but I'm going to round the horn and then kick out 15 because that bottom one's going to be all done modulo 16. So I'm going to take that. So it's going to be current message value, M0, XORed with previous checksum value, so C15. Well, C15 is still going to be all zeros. So when I XOR those things together, it's just going to kick out whatever M0 happened to be. So wait, not in the right world. It's down here. There we go. That's what I should be highlighting. So M0 XORed with C15, the last entry in C. That's just going to kick out whatever M0 happened to be at the start, which we know is the number 72, or that disaster in binary. So then I'm going to take that 72 and it's going to be shoved into that list S. So 72 is going to come in as my index. And then it's going to return back to me whatever lives at index 72, which in this scenario is going to be the number 148. So this thing is going to emerge as 148. And then it's going to be XORed with a 0. So my very first entry in my checksum is then just simply going to be the number 148. And you keep that process going on downward. So you're going to take that, move and move and move and move and move. In the next step, some things actually become a little bit more interesting because your previous checksum value now actually has some meat to it. So if I wanted to hand write that out, maybe we'll change colors. So I'll try to do it really small here. So if I wanted to generate what C1 is then going to be, so that's going to be coming from M1. So you're going to see that C1 is going to be the current value of C1, which is now a 0. And then it's going to be XORed with whatever S is going to kick out when I compare C0 XORed with what my current M1 value happens to be. So C1 is currently 0, and you're going to XOR it with S. So C0 was that 148, and M1 is what, 101? So you would take 101, you would XOR it with 148. That's going to give you a number. Then you're going to feed that into this list S. That thing becomes my index. List S is going to scramble that thing up, and it's going to kick something back to you. And then ultimately, you're going to XOR that thing with a 0, which is just going to kick out whatever that is. And I'm claiming that the output of that is simply going to be the number 68. And that's all you got to do. So that's all this cute little checksum is going to run, is that you're going to blast across this padded message. The way that you're going to compute the next term is going to be to take that current message, XOR it with the previous checksum value, scramble it up with this list S, and then update your checksum value by XORing it with what it currently is. So if we jump back into the code, we can kind of see how that operation is going to go down and then play around with it a little bit as well. Getting all excited, just jumping around, moving my hands around. I shouldn't be wearing a sweater, it's getting too warm now. All right, so hopefully we're back to here. So I have my giant big ol', whoa, S. Let me zoom back out because that got crazy. So down below, I'm just going to have a couple just formatting things. So I'm going to be eating things from the user. So if I go back, we're going to, let me give this another run. So we just have the traditional hello world up, which is the one that we have in the notes. All right, so what it's going to do is it's going to take that from the user, again, do all of the printy things. The first thing it needs to do, it needs to do this padding. So I'm going to compute the length of that thing, which happens to be 11, and then subtract that from 16, which is going to be stored as a 5. So I'm going to append 5 5s to the end. And then it's going to be the game of actually constructing the checksum. So it's just a little bit of looping and XORing over and over and over again. So I'm going to initialize my checksum as being 16 zeros. I'm going to have a last term, which is going to keep track of the last checksum value. I'm going to initialize that to be a 0. And then I'm going to have an outer loop and an inner loop. So the outer loop's basically going to tell me what block of 16 in that original message am I working with. Well, in our example, there's only one block of 16, so that's only going to happen once. But I might have 2 blocks of 16 if my thing is 32, or I might have 3 blocks, 5,000 blocks, some number of blocks there. Then the inner loop is basically going to do my pass across my checksums. It's kind of the way that I like to think about this, is that I'm going to update C0 and then update C1 and so on down that list. So the C0 is essentially going to live below M0, and it's also going to live below M16 and live below M32 and whatever version of 0 mod 16 we have. So the way that we're going to design this then is we're going to take the current M value, which is that one. We're going to XOR it with the last C value. So it's going to be stored as last. That's going to give me some number. That's going to be my index that I then jam into this crazy little list S, this permutation list S, or this lookup table. That's then going to kick out a new value, which I'm then going to update with my current C by XORing it with whatever it previously was. And then I'm going to restore that as my last, so I can keep on using that as I march on down this list. And that's it. So it's going to print out what my checksum happens to be, and then ultimately I'm going to append that to my padded message. So if I run this thing, you can see that hello world, and if I give it a whole bunch of exclamation points, my list now has length 21, so I'm going to have to pad on a whole bunch of 11s to make it up to length 32. And then we're going to do 2 passes of my original message, because I'm going to have to work with the first 16 and then the second 16. And it's going to generate this checksum. And then I'm going to append that thing to the end of my message. So I'm going to have a list plus pad plus checksum, which is going to be that thing. As I alluded to earlier, that could be a totally fine stopping place. There are many, many applications for just simple checksum algorithms, is that if I wanted to send this thing across some channel, I totally could. If you were to change any of those things, you would automatically be able to identify that an error has occurred. Basically, take the original message, run it through the checksum algorithm. If it doesn't match with what the checksum that was given, you know something funky has happened. So then you can ask basically, please give me the thing back, something occurred in transmission. It's not able to correct it like the error correcting codes could, but at least would give me the chance to detect that issue. So that's the middle guts of this MD process. It makes use of this nice little lookup table S. It's often referred to as a pi permutation or a pi lookup table. And the reason for that is supposedly Ron Rivas, when he was designing this process, basically took some of the digits of pi and then threw them into this thing. So there's a cute little formulation for how S actually came to be that does genuinely grab some of these pi things. But it is a thing that we have to keep. If you were to change any of those numbers, you would completely change the meaning of this checksum as well as the meaning of this particular hashing algorithm. So that has to be given and it has to be fixed. I can't go about changing any of those. I also have to do the padding in this way. I can't go about a different padding mechanism. Otherwise, it's going to compute a different checksum and it's then going to compute a different hash output as well. So there's a couple little nuances that we don't get choice in it, but it does give us a nice little starting place. So I'm going to pause this there, and then we're going to jump into the proper compression process and do a whole bunch more XORing. So we'll see a bunch of that goods come into play, and then we'll again jump up into our code and see what's happening there.